I can't answer the question. I'll just hope you guys find the answer. So, first question.
Honestly, I just wanted to go over one or two of the things again.
Yeah, you can start with that. I don't think I have final.
I got a question that you can do.
Okay.
That the worker carrying the source, he walks like 50 meters or something.
Okay. So let's say we have a point P here, and we have this is our geometry. Let's say this is 10 meters. And we're carrying a radiation source from here to here. The worker carrying it, he's traveling at 0.5 meters per second. Okay, let's say it's 2 meters. Does this sound like what you're asking?
Yeah. Well, for that one, if you want it at the point, I'm saying if the worker is like moving, if you want the dose at the worker, like the ambient dose equivalent at the worker, who's like just like 2 meters away, moving with the source.
He's like carrying the rod with him. So, or he's like carrying it held out like 2 meters in length. He was walking in like a straight line. Is that just like a point source?
Wouldn't that be a point source?
Yeah.
That wouldn't be. You wouldn't consider that a moving source.
Okay.
Yeah.
All right.
So then you would just count it as a point source.
Yeah. If you just have a worker and he's holding a radiation source right here. And it has 10 to the 10 photons per second, and his chest is 1 meter away.
Sorry for coming late.
No, you're fine. Yeah, this is just
pretty well. How are you? Happy to have that paperwork done.
1 second. I'm just gonna get that.
Me too, man. Definitely.
It's all right.
Yes, this recording's gonna be awesome.
So do you want me to go through this one?
Do we go ahead and do it one more time?
Want me to go through this one?
Sure.
Sure. So the way that we're going to do this one, we're going to break this up into 2 problems.
Which one is this?
It's just the example one where like a person's running with the thing, and we have a detector over here. How much dose does it get?
We're going to make this a line source.
So he's running this way?
There's a radiation worker right here, and he's running with a source. Okay. And there's a person sitting on a bench 10 meters away.
Okay.
Is this the homework problem where there's like a jogger or a source and just
source keeping?
A cancer patient's running by his friend.
Very cool. I approve.
Alright, so let's give this source, this point source, let's give this source a strength of 10 to the 12 photons per second, and they are 1 MeV photons. So we need to find the source strength across here. So he's traveling at 5 meters per second, or 0.5 meters per second, and he's emitting at this rate. So we need to find how many photons are emitted along this line. So if we have 10 meters is going to equal velocity times time, 0.5 meters per second times time. That means that this is going to take 20 seconds to get from here to here. Everybody okay with that? All right. So along this segment of line, this 10-meter segment, you're going to emit 10 to the 12 photons per second times 20 seconds across this line. So that's going to give you 2 times 10 to the 13 photons emitted across this line segment. Not the entire line segment, this line segment. So our line source, we're just gonna convert this into a line source. And we want this to be photons per centimeter. So 2 times 10 to the 13 photons over 10 meters, it's 10,000, or, I'm sorry, 1,000 centimeters. So it's gonna be 2 times 10 to the 10 photons per centimeter. Everybody okay so far? Okay. So this angle is 45 degrees, right? So what we're gonna do is we're gonna bring this up into a problem we can solve. So let's take let's say that this is x, this is positive x here. Starting at 0, and then this is 10. So let's take a differential chunk here and say that let's call this dx at position x. So the dose that we get is, is going to equal the source SL times Vx at that point times what's the radius? How far away is this? Well, we know that 10 over this distance, this r, is equal to cosine theta. Well, that's not really do much for us.
R
Did you
equals.
just do like
Can
10
find the
meters squared
cosine.
Yeah,
plus X
there we
squared?
go. 10 squared, 1,000 squared, plus x squared equals r squared. Thank you. 1,000 squared plus x squared, not actually r, x squared. So this is our source strength, the amount of source that's contained inside this dx. The line source times the distance will give you units of photons. This is uncollided, by the way. Then our geometric attenuation is just going to be the radius over 4 pi r squared. So this is times 4 pi. Okay, and let's put this in vacuum. I think I spelled that right. And there won't be any geometric or exponential attenuation. So to get this, just the total dose, you have to integrate from 0 to 1,000 of SL dx over 1,000 squared plus x squared 4 pi. So SL comes out, 4 pi comes out. You have integral from 0 to 1,000 of dx over 1,000 plus x squared, and that can be solved. There's transformation that makes this easier. Let me find that.
Right. That's what we have calculators for, right?
Yeah.
Numerical integration.
Yeah, if you have TI-89, there you go.
TI-89s are the devil.
There's a Wolfram Alpha for this as well.
Yeah, if you guys have your computers in here or whatever, you can use that.
Open resource, open node, not open neighbor.
Response function. Now, do we need to put a response function on this too, or?
If it's asked in the question. Yeah.
The dose.
Herpa derpa derp.
Yeah. So,
It's okay. We know the.
okay,
the
yeah,
end
there's
result.
there's a trig. There's a way to make this easier using trig, but you can solve that. So you get an answer. All right, next question. Anybody have any more questions than this? Just have the problem. Schultz likes these geometric problems where you get to turn into something similar. So your total dose is going to be, let's call this V1. It's going to be 2 times V1. Don't forget to multiply that through. Common mistake on this problem is saying that it takes 20 seconds to get from here to here. So we have 2 times 10 to the 13 photons. That's only across here to here. So you have to divide that by this distance. Don't take a number don't take the time that you calculate for half the distance multiplied by the source strength don't use that number to calculate the line strength across the entire thing. It's gonna take 40 seconds to go the entire way. Okay, so you'll have twice as many photons, but you also have twice as many distance. So your source, your line source will be the same value calculated both ways, but don't mix up those ways of calculating it. Stick with one way. A lot of people miss problems. A lot of people miss points in that homework. All right.
I have a question from a knowledge